Hi, this is Chaitanya, and the presentation is about fabrication of thin film transistors with carbon nanotube ink. In this presentation, we report on two topics about printed CNT TFTs. The first topic is about print fabrication technology and its reproducibility. The uniformity of the CNT TFTs is also evaluated. The second topic is about CNT ink development based on our print fabrication process. Various types of CNT ink were used for the TFT fabrication and their electronic properties were investigated. The key feature of print fabrication is simultaneous material deposition and pattern definition. It reduces the number of process steps and amount of waste materials and leads to low cost and eco-friendly fabrication. It is suitable to fabricate large area and low cost devices. Device fabrication flow. All device elements were patterned by printing methods with minimum number of materials. The surface energy and print conditions were arranged for precise pattern definition. The fabrication flow is shown in the figure, where a 75 micrometer thick polyimide film was used for the substrate. After the film surface was treated by the corona discharge method, gate electrodes were inkjet printed with the Nano AG ink unsintered. Next, gate insulators were formed using an ink dispenser with the polyimide ink and then cured. The average thickness of the printed PI was 630 nanometers with a standard deviation of 4.9%. Next, a 30 nanometer thick SiO2 layer was sputter deposited. Then, the source and drain electrodes were formed by inkjet printer with a Nano AG ink, and the average of channel length was 105 micrometers with a standard deviation of 4%. After modifying the SiO2 surface with 3-aminopropyl triethoxysilane, which is also known as APTES, the CNT ink was to cast the channel regions using a dispenser. In the drying droplet, the micelles containing the CNTs were actually absorbed to the APTES modified surface, and the CNTs could be deposited homogeneously even in the presence of the outward capillary flow. CNT preparation. CNT ink was prepared by purifying semiconducting CNTs by the electric field induced layer formation method. First, the CNTs with diameter of 1.3 nanometer were synthesized by the direct injection pyrolytic synthesis method and dispersed into an aqueous suspension with polyoxyethylene lauryl ether non-ionic surfactants. After applying a direct current electric field, the micelle containing the semiconducting CNT were extracted to the anode region. The estimated purity of SCNTs was more than 95%. The surfactants were removed from the channels using a combination of heat and wet treatments. The maximum temperature was 200 degrees centigrade during the fabrication. In this study, we used a sputtered SiO2 layer as a seed for APTES modification. However, reliable insulation is not required for the layer, so it can be replaced by printable materials such as hydrogen. Electronic property of printed CNT transistors. We fabricated two 10 by 10 TFT array samples on 50 micrometer into 42 micrometer PI films. Figure 2a, for samples 1, the cast volume of the CNT ink varied from 13.6 to 51 nanoliter, and a 17 nanoliter droplet was cast to each transistor in sample 2. Figure 2b shows the printed CNT TFT immediately after the CNT ink was cast. Typical transfer characteristics are shown in figures 3a. The characteristics showed the p-type behavior and an on or off ratio was more than 1000. A threshold voltage was minus 3.4 volts. Figure 3b shows the output characteristics, and the drain current showed saturation characteristics in the high drain voltage region. The excellent printed CNT TFTs can be obtained by the print fabrication. The relationship between the maximum drain current and the on-off ratio is shown in the figure 4. For sample 1, the maximum on-off ratio was more than 10,000 at ID max of about 10 nanoampere. The value of the ID max was critical and there was a trade-off between the ID max and the on-off ratios in the higher ID max regions. For the CNT random network TFTs, ID max represents the total number of CNTs in the channel, and on-off ratio is strongly affected by metal CNT contaminations. The current paths consisting of MCNTs were formed as the CNT density increased and consequently off-state current increased. The relationship between the ID max and the on-off ratio for sample 2 was entirely consistent with that for sample 1. This clearly shows that good reproducibility of this print fabrication. The uniformity of the ID max for sample 2 was excellent with a standard deviation of approximately 30%. The results were achieved by controlling the CNT network morphology with APTES modified surfaces. The average of the field effect mobility was 0.087 centimeter square per Vs, which was calculated using a simple parallel plate model. The field effect mobility was improved by a post-treatment to remove the surfactants from the TFT channels. It is thought that the morphology of the CNT network was modified during the post-treatment and decreased the CNT-CNT contact resistance, resulting in improved mobility. It has also been reported that Y-type junctions have low contact resistance between the CNTs, which leads to increased mobility. The inter-CNT resistance should depend on the additive agents of the CNT ink. Various types of CNT ink. Various types of CNT ink were prepared. The semiconducting CNT purification method ELF is available for a variety of CNT diameters and some kinds of polyoxyethylene alkyl ether as surfactants. Two types of CNTs with diameters of 1 and 1.3 nanometer were synthesized by DIPS method. Two kinds of surfactants, polyoxyethylene sterile ether and bridge 35, were also used to prepare the CNT aqueous suspensions. Then purifying semiconducting CNT by ELF and four types of aqueous CNT were prepared as listed in table 1. The aqueous CNT have enough surface tension to form the stable droplet on the solid surface. Ink 5 is an organic solvent type. After the semiconducting CNT purification by ELF, the surfactants were rinsed away from the CNT suspension by ethanol. Then the CNTs were dried and dispersed into a mixed solvent of xylene and dichloroethane using ultrasonication. Ink 5 contains only volatile materials except for CNTs. However, the surface tension of organic solvents is smaller than that of water, and ink 5 is rather wettable than aqueous ink. The aqueous type ink has the advantage of precise pattern definition in printing. CNT TFTs were fabricated with 5 types of CNT ink, and electronic properties were measured. The reproducibility of print fabrication was proven in the former experiments, and we can discuss the influences of the ink composition on the TFT properties. The relationship between ID max and the on-off ratio is shown in figure 5. For the 1.3 nanometer CNT ink, it seems that the influence of the kind of surfactants was insignificant, and the TFT properties showed similar trend for ink 1 and ink 2. For 1 nanometer CNT ink, the TFT properties depend on the additive agents. The TFT fabricated with ink 4 have lower on-off ratios than those with ink 3. The TFTs with ink 5 have larger on-off ratios and they have larger critical ID max than the aqueous link. In figure 6, the relationship between ID max and off-state currents, that is ID min, is shown. For ink 3 with surfactant of bridge 35, the trend was similar to those for ink 1 and ink 2. However, ID min took larger values for ink 4, with bridge 700, even in small IDMAX region. Bridge 700 has longer polyoxyethylene and alkyl chains than bridge 35, and it is supposed that the fragments of the surfactants are likely to remain and obstruct the semiconducting CNT contacts. Consequently, IDMAX was suppressed even though enough number of CNTs existed in the TFT channels. Then it is thought that the trend of ink 4 was shifted to the left side in figure 6. On the other hand, ink 5 contains no residual materials and IDMIN took small values. In addition, the critical IDMAX value is larger than that for 1.3 nanometer CNT inks. It may be due to the larger band gap of the 1 nanometer CNTs. These are suggestive results for developing the CNT ink to improve the printed TFT performances. The narrower CNTs is promising to reduce the off currents for higher on current TFTs, but device properties would be sensitive to the residual materials. It is important to eliminate additive agent from the TFT channel entirely when narrow CNTs are adopted. Further development and investigation for CNT ink and fabrication technology, such as surfactant removal process, are required. And I would summarize by we have developed printed CNT TFTs as a key device for printed electronics. Carbon nanotube thin film transistor arrays were fabricated on plastic films by printing without any additional patterning processes. All the device elements were directly patterned by maskless printing, and minimum materials were used for the fabrication. During fabrication, the morphology of the CNT random network was controlled by an adsorption mechanism on the surface to be printed, which resulted in excellent and uniform electrical properties. Various types of CNT ink were also used for the TFT fabrication, and their electronic properties were investigated. The suggestive result for further development of the CNT ink were obtained in order to improve the performance of the printed CNT TFTs. Thank you.